Hello, everybody. Welcome to the Hyperspace Challenge event forum series. I'm going to wait just a little bit for people to start coming in. Really glad to have you all here. Excited for today's topic. AI is always an interesting one. My name is Kelly Stafford. I am the Senior Program Manager for Hyperspace Challenge in Albuquerque, New Mexico. I am excited to introduce Meredith Schweitzer, who is also here. She will be my co-host from the Riot Mind Agency. She's our communications partner. And we are also joined by Parallax Advanced Research, Nate Hamilton, Kyle Dunlap, and Darrell Lochtefeld. Great to have you all here. Please, everybody, as you're joining, give us a shout out in the comments. We'd love to hear from you. We'd love to feature, just give a shout out on LinkedIn too, to one, company that wants to, oh, Meredith, can you go ahead and enable the chat for us, please, so that everybody can do that? Give us a hello and say where you're from, and we'd like to just give you a shout out on LinkedIn. If you want to just say hello, we'll pick one company to shout out on LinkedIn. So again, you should be able to chat now, everybody. And we are hosted by this event series is hosted by Hyperspace Challenge and also the Air Force Research Lab and U.S. Space Force. To strengthen the connective tissue between diverse communities within the space industry. The goal of today's event is to help the space industry startups get a better understanding of particular AI applications within the space industry and to talk about some predictions and trends in this area. So thank you guys for joining us. If you all would just give us a hello and introduce yourself first. Starting with Darrell.
Yeah, so I'll go first. I'm Darrell Lochtefeld. I've been with Parallax Research for 3.5 years. I manage our competitive research and development. So we do work for DARPA, IARPA, AFRL, NRL, you name it. If it's a hard problem within the Department of Defense, we're probably doing some research in that particular area. Most of our work is in command and control, artificial intelligence, and intelligence, surveillance, and reconnaissance. Prior to that, I worked 14 years as a civil servant. My last position was as the special assistant to the chief scientist of the Air Force. So I had the opportunity to sit in the Pentagon and see what AI was like there. And surprise, surprise, it was not exactly what I was expecting when I got to the Pentagon. And I'll talk about that a little bit further in the discussion. So that's kind of my background. I have a PhD in artificial intelligence. Nate, you want to go next?
Yeah, hello, everybody. I'm Nate Hamilton. I joined Parallax in the summer of 2022, and I've been an AI scientist at the company ever since. I work a lot in the realm of safe reinforcement learning and safe autonomy systems. So I'll be able to talk to some of that later on in the discussion, but generally the idea of how do we ensure that our systems are behaving the way that we intend them to. I got my PhD from Vanderbilt University, where I was awarded the National Defense Science and Engineering Graduate Fellowship and did my research in the same sort of field. Worked a lot with autonomous cars like this one I have in the background, and have been slowly transitioning into more of the space systems ever since. And go ahead, Kyle.
Yeah, thanks, Nate. My name's Kyle Dunlap. I am also an AI scientist at Parallax, and I have been working there for about 1.5 years now. Similar to Nate, I work a lot on safe autonomy, and I try to focus on real-time safety assurance for autonomous aerospace systems. I received my master's from the University of Cincinnati in aerospace engineering, and just before I started working at Parallax. Yeah, that's all for me.
That's great. Lovely to meet you all. So let's just dive right in. Darrell, do you want to just give us an overview of what Parallax is doing, broad strokes within the aerospace and space industry? and how you're applying AI to space applications.
Sure. Actually, I got to into it just a little bit with the introduction. Parallax really has two sides. We are a 501c3, which means we are not for profit. That also means that we are not considered a small business, but we are also considered a nonprofit, which allows us to compete for other work. So we've got about 40% of our work is in facilitation of small business working with the government. That could be anything from stuff that we do nationally with the Apex program, stuff that we do more on the state level with the Ohio Federal Research Network. And then we also have a program within the city of Dayton called Fly Dayton or Launch Dayton that does something similar for the city of Dayton. So we work with small businesses about 40% of our work. My work with Parallax is on the other 60%, and I've got a fair chunk of what Parallax does there. As I said, that's mostly command and control related items. For instance, Parallax has developed a large piece of software called Vigilant Spirit that's used for airborne command and control of drones. And is being rolled out to the Department of Defense across the department. We do things like space-based sensing algorithms, control of airborne drones, creating algorithms for space situation awareness, working on robotic solutions where there's very little margin for error. And even some more mundane tasks for the Air Force, like trying to figure out what we do for hiring civilians and how do we determine who is qualified for a job. So AI has got a variety of places that we use that, and that can go all the way from, again, mundane to very cool application.
Kelly? Right. Yeah, so you guys talk about, I know that I've seen the word intelligent teaming on your website, and I know, from past, I've heard that a lot of times. So how is that, how is intelligent teaming applied to the space industry today? And can you explain that term a little bit better than I did?
Sure. Sure. We love to think AI is some black box solution, right? That just sort of handles everything without human interaction. That is not the reality. I mean, even if you look at some very basic things like take a look at your phone. When you take a picture of something, you see these boxes that show up, and they're typically detecting faces or pets. What it's doing is it's auto-focusing for you, and it's showing you what what the camera thinks is interesting in the space. That way you can either overwrite it or take the picture as is. If you don't have a human interface, the reality is AI is only as useful as it's trained, and it doesn't do a great job of providing context and those sorts of things. So when we think about intelligent teaming, it's a combination of both humans and machines, and that can be anything from a machine playing or working with another machine, all the way to a machine working with a human. There's a lot of groundwork that goes into developing AI, and if you don't have a good interface for the AI to work within and around, oftentimes these systems fail, not because of their performance on the given task. They might be great at detecting something, but they fail because of human adaptation. So when I say intelligent teaming, I mean all of those aspects. We have a research psychologist, for instance, on our staff because of the fact that it's not just about technology, it's also about technology adaptation and how it's used. Back to you, Kelly.
Okay. Yeah, that's really great. So Meredith, did you have something you were going to ask?
Yeah, I'm really interested in this idea of like merging human and programming. I know that like the MIT Center for Collective Intelligence, they do a lot of work around that, and I think one of the things that that they talk a lot about, which I think has to do with Nate's work, and I might have Nate and Kyle, I might have you guys flipped, but I'm really curious about where where these ideas of like intervention for safety purposes come in. I think that might be later in the question, so I might be skipping ahead, but it just feels kind of like a natural, you know, a follow-up to this idea of the teaming. I'd love for Nate to talk about like real world applications of where you have to integrate, you know, human intervention for safety purposes. I think that's really interesting.
Yeah, that is very interesting. And like one thing that I don't know, I'm pretty sure this came out in the news just this morning, but Tesla rolled back a bunch of recalls for their software with the autopilot, and saying that people are too trusting of this particular software and that we need more human intervention on this AI system. And so that's broadly where the realm of safe reinforcement learning tries to fit in, is like, how do we ensure that our systems are behaving the way that we want them to, that your cars aren't crashing into other cars, that I've got this autonomous car right behind me, that we're not crashing that one into walls, is one of the main concerns with that particular device, or with spacecraft, that we're not crashing those into each other, because that's a really expensive issue if that happens. And so there are many routes that we go through in order to provide this sort of assurance. Kyle is very much the expert on those different techniques, but one of the ones that I'm most familiar with and easiest for me to describe is the simplex architecture, where you've got one backup control that's verified, and then you've got your primary control, so like your RL, your AI, your machine learning, something that has very high performance, but you're not sure that it will always behave safely. And then you've got your backup control that has lower performance, but it has those guarantees. And so the simplex architecture switches between the two when it identifies that the primary control is starting to fail. And so one way you can think of this is, I don't know how many people here have done in-cars, but that's like part of the driver's license process here in Ohio, where you have an instructor and the learning driver in the same car. The instructor has their own set of brakes. And so as you're learning how to drive, you've got some supervisory control that's able to intervene and like to step on the brakes whenever they think that you're going to be doing something that would put the car and themselves at risk. And so these safety systems are much like that driving instructor, of being able to protect the system from violating those safety constraints throughout the training process or throughout deployment. Kyle, did you want to add anything to that?
Yeah, sure. Another great example that I like to think of is the automatic ground collision avoidance system for fighter aircraft today. And that's the case where if a pilot might lose consciousness while they're flying, and they started maybe diving to the ground or something, then the auto GCAS system can kick in and intervene and stabilize the aircraft such that they don't actually collide with anything. And I think this has accounted for at least 9 saves of pilots or aircrafts today. So it's really useful to have these types of systems, especially in aerospace systems. So it's great to have that trustworthiness from the pilot too, to be able to trust that there's this safety assurance system that they know is there, and they can still fly the aircraft as they usually would, but they can let the safety kick in if absolutely necessary as well. So I'll pass it back to you, Meredith.
So let me jump in real quick on that. Some interesting things about the auto GCAS, for instance. When it was first implemented, the pilots didn't trust it. And they actually thought that it shouldn't be there, that it was telling them how to fly, that it wasn't a necessary function in the plane. So if you're looking at intelligent teaming, what happened was this one team member didn't trust the other team member to do its function. And it wasn't until a couple of saves started to go by and pilots actually understood the system a little bit better that they started to adapt it and actually recognize that it was useful. And that's what, brought it from a single aircraft to multiple aircraft within the Air Force fleet. So there was a significant adaptation, if you will, of auto GCAS, both in understanding when it kicks in, why it kicks in. There was, significant studies done on the human interaction side of things to make auto GCAS successful. You can think of that same thing on the self-driving cars. If you're in a lane, right, and it tells you that it's detecting that you don't have your hands on the wheel, that you're not pulling the car one direction or another. It's giving you some feedback saying, hey, wait a minute, now I expect the operator to be alert and attentive to what's going on with the car, even though it's automatically staying within the lane.
It's like conversations, like you have to build a trustful conversation. Yeah. That's so interesting. This idea of trust is like so interesting. And then I'm gonna hand it back to Kelly. I know I'm like taking over, but I'm really curious about where you see that trust, that question of what to trust and not to trust in space applications more specifically. I can see the like pilot and the driver of a driving car, but in spaces where we have become so accustomed to being in situations where we just have to trust because there's no access right to the machines. Like, so can you like kind of go off of that thought of how does trust with the systems play differently in space applications?
So first of all, one of the things is you don't have the literal sensing and you're not necessarily in the loop. So that is an issue. Typically, models that are built off of artificial intelligence aren't very accessible. And so that can be an issue. You've got a deep neural network and you're expecting it to perform a certain way. But what assurances do you have that it's actually going to perform in that way? There's ways of matching, if you will, what the current situation is against what the neural network was trained against. And if it's not matching very well, you should have less assurance or less trust in that model. And so you can start to build models around the trust based upon what data you've already trained it against and what situation you're currently in. So there are some ways of handling that. I'll say that that's a deep area of research. There's a lot of work that can be done in that area, both in terms of going to more trustworthy or transparent models, as well as providing safeguards, if you will, for the models that are a little less transparent to make sure that you understand why they're working the way they are. And then how do you display that in terms of a human interaction and tell the human that the model is off the rails? Models tend to not have a confidence about their confidence. They tend to give you some confidence values, but they don't give you a sense that they're really out of the place of their understanding. They don't have a good sense of sort of a meta model, if you will, of their own cognition.
Yeah, that's interesting. So just curious, just building off of that. So what are some of the other challenges, that you guys face in building this technology? And, just space is difficult because, we can't test directly. So exactly, like what challenges are you facing on a day-to-day basis?
Nate, do you want to go over the Cinderella component here?
Yeah, that's exactly the kind of point I was hoping to make. Is there's this huge difference between the simulations that we train these AI systems in versus the real world. Like, I constantly go back to car examples because it's one thing I'm super familiar with. But like in simulations, you never have wet road conditions, but in the real world, the roads are constantly wet or they're covered in snow. And so in those scenarios, you can't trust your AI to perform as expected because it's completely outside of the domain that it was trained in. And so that's one area that's a big challenge, is how do you identify when your system is no longer in the domain that it was trained in? And then how do you adapt its behavior to maintain performance in those scenarios? Because you can't just go, uh-oh, we're in a new scenario, I need to train a new neural network to handle this as fast, like if we're operating at 10 times a second, you can't train a neural network in 10 seconds to now provide a new control system. And so like that's a big challenge within the space, is this going from really good performance in simulation to the same kind of performance in reality. And that's why we see so many papers that are more focused on like video games, because it's all simulation.
So what are some of the ways that you, solve those or mitigate those issues?
Yeah, that's actually a big research question within the field right now, of like, how do we bridge that gap? And one of the main approaches that Kyle and I are involved in are the runtime assurance techniques. So providing that instructor for your AI as it's operating in the real world, because you know that when it reaches those out of domain scenarios, that you've got some fallback that is trustworthy and will get you back to some particular space that you can count on. So in the example of humans that are learning to drive, that's usually a stopped position. But in space, maybe that's reorienting the solar panels towards the sun and pointing communications back towards the ground, or going out to some sort of parking orbit if you're trying to do some docking maneuver. Kyle, do you have some other ideas on that particular space?
Oh, I think you hit them all there. But yeah, like you said, this runtime assurance is really helpful for deploying our AI in the real world, and it helps us separate the tasks of performance from our AI systems and the task of safety, which we can ensure through runtime assurance. So by decoupling those two aspects, it can make it a lot easier to get our AI into the real world.
Let me add, there's probably no replacement for good engineering here. What do I mean by that? Well, let's look at the data set. While our data set doesn't have water in it, or doesn't have particular effect in it, how do I mitigate that effect? Well, let me try to add additional data to it. So you're constantly doing that on your models, right? The models are only as good as the intuition and the data that is presented in front of it. And so you're going to look for newer, interesting ways to augment that. Let me give you a kind of a real world example. Suppose we were trying to find or detect cars, say, over a city, and we had a camera that was from space looking down, and we wanted to be able to put a box around every car. That might work great until it snows, and now the cars have some amount of snow on them. And how well do we detect those cars now? Right? We may not have simulated that case. We could have simulated that case. We could have envisioned it. And so a part of this is about, good practitioner, logic, thinking about those things ahead of time, getting a sense of what performance characteristics we're actually going to be in versus where our data is at, because we may not take pictures very well or often of snowbound landscapes. And so the AI algorithm just doesn't have a good truth set to start from. Over.
So I'm just curious. So this is all very interesting, and I'm just curious how you guys learn, where to move forward. What challenges need to be overcome. Where should research go? Where do you learn about the needs of the government, and how do you tackle that part of it?
So, in terms of the needs of the government, I'll say this first of all. The government classically is not a very good purchaser of AI. They have problems they want to solve, and oftentimes it's easier to look at the problem they want to solve and see if you have a solution for that problem. Vice, have the government come to you and say, "Hey, I think I need AI for this particular solution." The reason why I say that is oftentimes the government has no sense of have they even procured their data in such a way that it can be used for AI? Have they laid the groundwork necessary to do AI? I mean, there's a lot of movement afoot within the government to do those sorts of things. You know, most of the services, for instance, now have a chief data officer that is just designed to help structure their data and get it into a place where they can actually start to look at it. But the DoD is still grappling with those problems, and you know, generally speaking, the government, I'll say, is a little behind on what's going on with AI relative to other purchasers. And so a piece of this is about education, educating the DoD as to where you know, this particular technology could be used, how it could be used. The problem is oftentimes I see a lot of salesmanship and not a lot of delivery of actual capability, because it's easy to sell a concept that doesn't necessarily have the structure behind it, or the well-defined boundaries required for AI to be successful. So it is an art. It's an art from a government perspective. When I had my government hat on, figuring out what was real and what was fakeware, and there was a lot of fakeware pitched to me. I'd say it was probably 4-to-1 to realware. And figuring that out as a government purchaser was difficult, but it was also difficult to ferret out which, you know, contractors had real things. I had to ask a lot of hard questions over and over and over again until I got to a convergence of an answer, right? So it was, tell me a little more about your data. Tell me a little bit more about your data. Tell me a little bit more about your data. Now, how does your algorithm work with that data? Now, how does that data work with this, you know, system? And where do you think this is going to fall apart? And, you know, you ask lots and lots of questions, and eventually you can ferret out, you know, who's really got it there. But it's a difficult thing to do, and it's something that generally the department doesn't do very well.
So how, that's an interesting question. So how do you demonstrate your capability? I mean, specifically, I mean, a tip or any kind of, you know, anything you can offer to the small businesses out here who are trying to get that business. How can they prove that they are capable?
Well, so the first thing I think you want to do is you want to find somebody that's sympathetic within the government to that particular area, right? And there are some people that are decent purchasers, but not everyone is in that space. So finding who that is usually means you got to do some research. Digging into who's been publishing in that area is one way, for instance, or looking at the structure of an organization. Going to certain threads of that structure, like the chief scientist thread versus or chief engineering thread, depending upon what type of office you're engaging with. If you're engaging with the head shed, you're not going to get a good answer. That's a good starting point to get you to the engineer. But really, we want to get down to an engineer before you're going to get people to buy off on a solution. And so that's no, it's not an easy thing to work with the government. I'll tell you, sometimes the easier thing to do is actually work with a prime contractor. If you look at, you know, the largest, General Dynamics, Northrop Grumman, Boeing, et cetera, et cetera, et cetera, you know, you can list off all of the top 100 DoD contractors. What you're going to find is that they have requirements for using small business. And that requirement is usually at least 10% of their business has to go back out to a small business to solve problems. And so oftentimes you're going to find a technologist easier in a prime than you're going to find it in the government. You're also going to find in the government that they're going to turn back to their prime anyway for the discussion because they don't want to let a new contract. That takes a lot of time and effort on the part of the government for usually what is a component to a sub-component of a technology, right? So, you know, I would argue you want to spend more of your effort probably talking and engaging primes than you want to spend talking and engaging the government, and the primes will lead you back to the government if you've got a good engagement on the prime side.
That's really excellent. A really excellent tip, I would say. Everybody take note. I think that's really great. Nate, did you have something to add? I saw you can't. Did you come off mute or were you already off?
I just never let myself off.
Oh, okay. Sorry. So I'm curious from you all. Oh, Meredith, go ahead. You came off mute.
Oh, you go for it.
Okay. So I'm curious, where do you all see the future of AI in space? I'm just, where are we trending?
Like in the next like 5 years, like
Yes.
short-ish term.
So I'll start it with this, and I'll let Nate and Kyle jump in for commentary. First of all, you know, we'd like to think AI is further along in terms of actual deployment within space. There are some places that we are using it, and there are successes, and I'm not doubting that in any way, shape, or form. But I'll tell you, oftentimes, if we can get away with a microcontroller and a set of sensors with some basic signals processing, we're going to do that every time over sophisticated artificial intelligence, because of the safety levels required. And so you really got to lay some foundation work on the research and development side if you want to use AI in space successfully, especially for very critical missions. You know, every ounce of fuel on a spacecraft is a very precious thing. Just even doing space logistics, for instance, and figuring out how to resupply these things, again, a very expensive thing. And so we're generally going to go to the tried and true method, and we're going to keep it simple. But that's not to say that the AI can't solve some of these problems. I think there's a piece of this which is laying that foundation. Part of that is the sim to real gap in overcoming that. Part of that is runtime assurance that Kyle can talk to. And so if we do some of those well, people will have more trust in AI for these applications where they're doing a high stakes maneuver or high stakes discharge of energy, for instance, that you don't want to get wrong even the first time. And until we do that, I think space is going to be a little bit reluctant to see that. And where you're going to see AI used a little bit more is going to be on the ground at first, partly because of also hardware concerns and constraints. That said, for instance, the Department of Defense is investing very heavily in, you know, in architectures for compute. And so there are some trends that will tell you that, you know, AI is going to be pushed up into space. And I think that will continue. But there's some obstacles to that, and I'd say the main obstacles to that are like the runtime assurance type stuff. So, Nate, you want to talk a little bit more about, or actually maybe Kyle talk a little bit more about RTA?
Yeah, of course. Yeah, like Darrell said, I think one of the main things that we're going to be doing over the next few years is probably testing and trying to prove to operators and people who use these systems that our AI is trustworthy and is safe. And one of the ways to do that is with runtime assurance. So at a high level, RTA is a real-time safety assurance technique, and it's completely agnostic of the underlying control structure. So it can be plugged in and used with either a human operator on the ground controlling a spacecraft, or it can be used with our AI controllers. So it can be used interchangeably, which is really helpful. And I think just for the space industry, RTA is so useful due to the high cost of everything, the high cost of fuel, the high cost of the assets. So we need to be able to assure safety for those. And RTA is a really good candidate for being able to do that. So it's really important that if we can design our RTA well and we can test it in space and prove to people that it is safe, then it just adds an extra layer of verification and trustworthiness for our AI as we move towards integrating those pieces into the real world as well. So I'll pass it to Nate next if you have anything to add.
I don't know if I have a terrible amount to add. I know that OSAM on orbits servicing and manufacturing, is that what the M stands for? Or is it maintenance? It's manufacturing. Yeah, I know that's a big dream, and whether or not we'll be able to reach that in the next 3 to 5 years is kind of dependent on how well we're able to get our initial tests going. But I think one of the more reasonable goals in the near future is to start utilizing AI as the tool that it is. So instead of having a team of people controlling one satellite, you can have one person controlling multiple satellites, and just providing that high level direction of, I need you to go to this location and do this task, and being able to trust that it will be able to do that reliably. And I think that's something that's something that we're hoping to get to in the next couple of years.
So
So-
you see some power in scaling, that it like enables scaling basically and that's really interesting. We did this interview maybe 2 years ago with a researcher who had gotten involved in a contract through Hyperspace Challenge connections and work, and brought up the fact that coming out of academia, he had sort of assumptions and ways of thinking. And then when he came into contact with the procurement officers, he was like, well, let's imagine that we have like 1,000 sensors, and the procurement officers like, you have 6. So you have 6, like work with 6, and let's assume that we have these ground controls. No, you have 1 spot for ground control. Like what, and that has really stuck with me in terms of thinking especially for small businesses who are, or for people who are coming out of academia, like have these sort of visions of what can be possible. I'd love to hear, especially like Kyle and Nate, like coming out of grad school pretty recently, what coming into practical applications of this work have you had in a similar kind of vein of that narrative, or that kind of experience?
Yeah. One recent thing I can think of is we've been working on controls for various satellites using reinforcement learning, and we thought we'd come up with some great solutions, and then we gave it to some operators, and it turns out that our particular controllers were using like 20 meters per second of delta V to do this various task, and they're like, that is way too much. That's like an entire year's budget. You should be doing this on like 1. I was like, oh, that's how much that's limited. Okay. So yeah, that's been a major shift for us, is just the importance of that fuel use, and trying to minimize that as much as possible. Doesn't matter what your task is, if you can't do something else after you've done it, then what was the point of doing that task? Yeah.
Kyle, do you have one?
Yeah, I totally agree with Nate there. I think coming out of grad school, we do a lot of fundamental research, and we apply our algorithms to simple tasks that maybe aren't very realistic. So it's a big jump getting into problems that actually matter. And like Nate said, just discussing with actual spacecraft operators what our solutions look like, and figuring out those gaps between our current knowledge of the problem and how things work in the real world. That's really critical in making sure that our algorithms are usable.
Can you tell us how you guys get in touch with those operators? Like, how do you reach the customer?
So I would say that that's mostly handled by our government contacts. So I'm not sure I have a great answer there. But if Darrell or Nate, you guys have something to add too.
So I'll just add that there are a couple of ways to get a hold of customers, and it depends on how you're doing it. If you're working with an integrated government agency like AFRL, it's usually best to do that government to government rather than contractor to government. But you don't always have that luxury, especially if you're, proposing an effort like a CIBR or SITR, something that's a small business initiative, and you need to reach out to the customer directly. There are a couple of businesses that actually make their business model such that you connect to another a government agency through them. There are companies out there, for instance, that will just go out and hire retired colonels or hire retired analysts, and their job is to provide access to those customers. And so sometimes it's better, especially if you're talking, learning on the job, if you will, like I'm going to do a server phase one, and I'm going to learn some things about what's going on in that phase one process, and then I'm going to go to phase two to let a small subcontract in as a part of that, just to get you access to those customers or access to that area of the government. And there are companies out there that do that type of connectivity sort of work.
That's great. That's really good. Okay, so wrapping up, I just want to start asking the Q&A. We got a couple of questions in the Q&A, but first of all, I want to know, we've already kind of touched on it a little bit, I think, but who do you partner with? And how do you work with small businesses? Do you work with small businesses? And, like, what kind of partners are you guys looking for?
We do work with small business. We do quite a bit of work with, DARPA and IARPA. And when you're going after these larger efforts, like an actual DARPA program, that might be, I don't know, say, I'll just use a notional $10 million a year. Parallax will provide a core service to that, and then we'll look for partners, whether they be an academic partner or a small business partner, to augment where we are missing things. Let me give you an example. Parallax does not do heavy computer vision processing. So if we need a computer vision processing partner, we'll find that partner external to Parallax, because that's not our core business area. And so, generally speaking, for these large bids, you get one of two sort of competitions that come into DARPA. You get a large prime like Northrop Grumman or General Dynamics, or you name it, that has so many different business units that they can just tie their business units together and say, hey, we've got the 90% solution within the prime contractor itself. Or you have these smaller organizations like Parallax that create a consortium or team, usually involving 3 to 5 key team members and an academic team member, to go after that particular problem. And so that's been our business model, is we will look for other team members that are interesting in that space. And usually what I do is I keep a Rolodex of, who complements us really well in different areas. And then when a solicitation hits the street, and I get a chance to look at it, we'll call up, the people that are in our Rolodex to figure out how to create a team against that particular problem set. So a piece of that, by the way, is come talk to us, and if there's a fit, we'll be happy to hear it. We've got, for instance, a set of people that work on natural language processing, because that is not our strength either. Now we've got some people that know NLP, for instance. We've got people that know transformer models, but we're not. We didn't create ChatGPT or DALL-E, for instance.
Right. Okay, that's great. So Meredith, were there some questions in the Q&A? Let's see, what do we got here?
Some of them we've kind of answered, but I think, let's see, I'll just read this one out from Chelsea. She's asking, let's see, the theme of advanced air mobility and its impacts on the 16 sectors. How do you see this information applying to the AAM and critical space or critical infrastructures in space? Those are so many words that I don't know. So does that mean anything to you?
Yeah, so I can probably take that. There's a lot going on in AAM right now, advanced air mobility. Those are sort of flying cars or flying taxis, concepts for point of delivery using drones within the United States. How that translates to space activity. Obviously, there's a problem in physics that makes the space activity a little bit more expensive. It's hard to put weight up in space. And so I don't know that it's as clear how that transition might take place in the future. I do think there are probably some lessons learned there. If I'm looking at the problems in AAM right now are largely driven by policy, not so much by technology. Until we get out of our way, if you will, on the policy side of things and determine what kind of lanes, what kind of UAVs can fly in, and how do they gain airworthiness, and how do we support them in terms of infrastructure. How do we handle pilot licensing, because it's going to have to be different when I have to do it at a large scale versus a small scale. Those types of problems are not yet solved. And I'll say that I think as far as AAM is along the learning curve, the space community is even further behind it. The space policy, for instance, is not even clear necessarily who writes all of that policy in all places. And we're still standing up a space force and figuring out what space looks from a military perspective versus what it looks like from a civilian perspective. So there's a lot of moving parts, I'd say, and I don't think most of those moving parts are going to fall in the technology restrictions. They're going to fall in policy restrictions.
Darrell, I'm in this debate with someone right now about which is a greater bottleneck, the workforce pipeline or the regulatory constraints. Where do you land on that?
In terms of AAM or in terms of just in general?
In terms of really forwarding, I think within the context of this conversation of forwarding potential AI applications to technology, space technology in particular.
I would argue the places that we have bottlenecks are first in, and I don't know which order they could fall in, but first in policy and second in ethical use of AI. The workforce is interesting because the larger the workforce, the more depth that the workforce has, the more novel solutions you're going to get to some of those other problems, including policy and including the data problem. But I would argue that the data problem and the policy probably drive also the workforce involvement. So if I'm looking at it, the workforce involvement is probably a secondary consideration, and the primary considerations really are, where can we apply our AI methodologies where we have the right amount of data and the right environment and the right amount of compute first. And then the second one is are we ethically restricted to be able to do those things?
Where do you all land on that, Kyle and Nate, on more ethical, more constraints around ethics or less? I mean, where do you land there?
Personally, I think because I'm coming from this safety background of, I think there should be more restrictions on safety aspects, because I don't know how many of those Tesla videos you've seen of them just plowing through test kids, in scenarios of that's probably not something that we should have on our roads that isn't being monitored by humans, because people are too reliant on the technology as it exists. And so in that regard, I'm I lean more towards we should have a bit more regulation, a bit more oversight on some of that stuff, but at the same time, a lot of that oversight just becomes really dumb and useless. And so there's that balance between the two of we need to make sure that these systems aren't going out and killing people, but at the same time, if you stop them from doing anything, this is an example from the formal methods community of safety versus liveness. Of if you've got a car and you want it to go from point A to point B, the safest control is to not have the car move, but that doesn't satisfy the liveness of going from point A to point B. So your super safe controller doesn't achieve the objective, but your super capable controller might just drive through buildings in order to get to point B. And so you got to find that optimal balance between safety and liveness in order to ensure you're meeting both requirements. I hope that answered the question.
And it's interesting because it kind of goes back to that trust, the trust we were talking about earlier. It's like, okay, how much trust is too much trust? You don't want to have too much trust in it
Yeah.
and not enough either, too. So that's interesting.
Yeah, Kyle, what do you think?
Yeah, I completely agree with Nate. I was going to bring up the safety versus liveness debate as well. Because if you can build your system to be really safe, but you have to have that balance with liveness such that your safety assurance system doesn't become overly conservative or constrain you from being able to complete the problem that you really want to complete. So it's really important to find that balance. And going back to the auto GCAS discussion that we had at the beginning, it's really important to have that balance there, where specifically pilots didn't want the safety assurance to kick in too often or too soon or anything like that. So they wanted it to be minimally invasive and ultimately make sure it assures safety, but make sure that we can still complete our primary task and fly the plane without intervention. So it's critical that we have that balance in safety and also in ethics.
This kind of is a follow-up to that almost. So Jason's asking about sort of the academia versus industry side of here, I'll just read this to everyone. So he's saying, in terms of academic industry focus and the money question, it seems the majority of the work on the performance, capability, results of models versus explainability and safety. Even on performance, most academic papers aren't even truly reproducible because they don't save random seeds for training process, even if they provide models and data. In the field of RL, I've seen papers that say TD3 is superior to SAC on benchmark tests and others that say SAC is superior on the same benchmark test. So the question here is, what can government, industry, and others do to incentivize focus on explainability, safety, and reproducibility of results to kind of establish like best practices? Like what's going on there that you think's important? Maybe.
I can talk to this a little bit because I'm from the RL community and I know exactly what you're talking about with TD3 and soft factor critic having reportedly different results and that lack of reproducibility. And there's a driving force within the machine learning community and at all of these conferences. Like NeurIPS now requires that you provide code, and there's a more and more incentive in order to get published at these top conferences to provide code that is reproducible. I don't know if you've seen some of the more recent papers. They'll have like little badges that say this code is reproducible or these results are reproducible. And I think as long as we're continuing to push forward that you can't be published unless we can reproduce your results, that's a great way to get academia and a lot of some of the industry that's publishing papers to make that focus on reproducibility. I know that's something that I've been pushing for in a lot of my work, is that if it's not reproducible, it doesn't exist.
I will say that academia has a bad precedence of pressure for what is the most quantifiable measures, not necessarily the best measures. We look at significance in terms of, a statistical score as opposed to looking significance in terms of actual real differences, right? So I can say something is 0.001% better, and I can say it's statistically significant that's better. And those types of things get published despite the fact that maybe I actually lost on other dimensions like reproducibility, like understandability. And so we can do ourselves a disfavor by, if you will, focusing on those numbers. But I don't know how to change the classic structure of academia to some extent outside of, occasionally seeing a journal that's willing to accept a paper that's more around, hey, look, on these soft factors, I'm better and I'm no worse on these hard factors, right? If you can get journals to start to accept those kinds of papers, then you can change the way academia starts to think about this problem.
All very good. Okay, so we're running on time now. So I'm gonna go ahead and start wrapping it up. Thank you guys. It's been super informative. I know that everybody on the line probably got something out of this, and we really appreciate your time and your expertise. You guys are just a wealth of knowledge. So it's been great to have you here. For everybody else, if you enjoyed this discussion, please go sign up for our mailing list if you're not already. And so that you can be up to date on the latest events, on our next challenge, be up to date on what's happening with Hyperspace. And that is at hyperspacechallenge.com. Our next webinar will be after the holidays, January 11th at 10 a.m. Mountain Time, and we'll be talking to the Catalyst Accelerator, which is one of our sister accelerators out in Colorado Springs, and they have just started accepting applications for their next cohort, which is on the topic of space domain awareness. So you'll want to tune in if you want to get some questions answered and just learn about what their program is like. It's an amazing program. People get so much out of it. It's I think it would be great for you guys to tune in. And then also follow us on LinkedIn and Twitter. And this program, if you want to, go back and listen to some of those little nuggets, those little tips and things, we'll have it posted on YouTube, and you guys can all just go watch, watch it over and over and over again. We want to get our hours up. So anyways, with that, I'm going to say happy holidays to everybody who celebrates, and we will see you guys back here again at the new year. So thanks again, and have a great day.
Thank you, Darrell and Kyle and Nate. Thank you.
Thank you for having us, and happy holidays.
Thank you.
Thank you for having us.
Bye, everyone.